Good morning. Z-plane analysis of discrete time control systems. We will have try and understand what is how do we analyze Z transforms when you are applying them to discrete time control systems. Most importantly, we can understand that Z transforms are used for single input, single output discrete time control systems, where it can be used easily to obtain the output of any single input, single output discrete time control systems. And before going into this one, we are trying to understand that we are using a uniform sampling operation throughout the sampling operations that are used must be uniform. That is, the sampling period t must be a constant, and we have all the sampling operations at any point of the system. That is, if you are having a large scale system or a multiple loop system, large scale systems where you have many time constants, a large scale system might have many time constants, and the time constants are not equal, they are varying from different loop to different loop. Therefore, you will not be having a particular Z transform. Therefore, you should be in a position to synchronize. You should be in a position to synchronize all these time constants, so that if you are sampling at one particular rate, a particular loop, the other loop also must be synchronized at the same thing. Otherwise, at the same with the same sampling operation, otherwise the system might get distorted. The signals might get distorted. Therefore, that is very important for us to go with a uniform sampling operation and with a time constant t. For this particular thing, we are going to understand what is impulse sampling and data hold. Impulse sampling and data hold is the prime important, is holding prime importance in dealing with Z transforms. Right. So we'll try and understand what is impulse sampling here. Impulse is nothing but any function that is existing at time t is equal to 0. That is an impulse function del of t. Del of t is equal to unity. For example, a unit impulse function for all time t is equal to 0, and impulse magnitude is equal to 0 for all t not equal to 0. You can directly write this. You can write it here. You can simply say that at t is equal to 0. That is impulse sampling. You are having a function which is unity, a unit impulse function which is having the magnitude 1 at t is equal to 0, and the remaining values t not equal to 0 or t is equal to 1, 2, 3 so on, and minus 1, minus 2, minus 3 so on. The value of the impulse function is 0 for all time t not equal to 0. So for this, what is the Laplace transform of del of t? We know that it is equal to 1, and in an impulse function, and a Laplace transform of del of t minus t, you can say it is e power minus st into 1. That is what we have tried to. We already know about Laplace transforms in dealing with impulse signal. Therefore, keeping this in mind, we can try and understand Z transforms with this structure. For example, if we are having x of t as our unit signal, as our continuous time signal. For example, this is our continuous time signal. It exists for all t greater than or equal to 0. Is continuous for all time. X of t is continuous and exists for all t greater than or equal to 0, and below t less than 0 the signal doesn't exist. That is what we are trying to assume in this particular case. And this signal, this is already understood by us. We are having this as a sampler, which is a rotating switch, which may not be existing in the real world, but we are trying to use this type of function for mathematical representations. Therefore, we are going to use this as a sampler. It is a sampler with time period t. That is, it is a rotating switch at a particular time, at an instant. If it is in contact with this signal, then you are having the value, and immediately after the contact it is disconnected, and it will take one rotation to again come in contact with the other part of the circuit. Therefore, for sampler, this is sampler with sampling period t. This is the sampling period t. Therefore, the result of this, you will get it as x star of t. It means that this x star of t is an impulse. It is an impulse signal. Impulse signal. That is, if you can understand that if you are having a signal like this, at time t is equal to 0, at time t is equal to t, 2t, 3t, 4t, and etc. You have this value. You can say that at time t is equal to 0, the value of the impulse value is so and so, and at time t is equal to capital T, the impulse signal is this so and so, and so on. At time t is equal to 2t, the impulse signal is so and so, and time 3t. So this sampler will help us in getting this signal. So you can say that at any particular instant you are having the value. You can say this as x star of t. X star of t. That is the signal which we are going to get here. So that is only at various instants, uniformly divided time axis. You will have values of the magnitudes of the original continuous time signal. Therefore, you are having an impulse signal. So it is very important for us to learn. You can also call this as train of impulses, because it is a series of impulse signals clubbed together to infinity, up to infinity. Therefore, you can call it as train of impulses. So train of impulse, that is why we have already discussed about the Laplace transform of an impulse signal, which is giving us, this is del of t. The value of this, if you call it as del of t, you can say, and the value is x of kt, x of 0 at that function, so x of 0 into del of t. Now at time t is equal to capital T, you have this as del of t minus kt, and its magnitude is x of t. So you are multiplying a train of impulse signal, an impulse signal at a time delayed function into the original continuous time signal at time t, at time 0, at time t, and if you are multiplying these two, then you are getting a train of impulses with different magnitudes at every different instant of time. Therefore, you are getting a train of impulses, that is an impulse sampler. An impulse sampler, if you call this as an impulse sampler, the output of the impulse sampler is a train of impulses. The output of impulse sampler is train of impulses with magnitudes equal to the value of, with magnitude equal to the value of continuous time signal x of t, with value of continuous time signal x of t at that particular instant. At that particular instant. That is what we are trying to say. See here, any continuous time signal, if it is applied to an impulse sampler, you will get a train of impulses. That is what we are, the output of an impulse sampler this is the sampler, and the output of impulse sampler is train of impulses with magnitudes. What are the magnitudes of this output of the impulse sampler? You are having x of 0, x of t. Here you have x of 2t, del of t minus 2t. Here you have x of 3t into del of t minus 3t, and so on. Therefore, impulse signal which is delayed, impulse value which is delayed, and the magnitude of that is the value at that particular instant which you are trying to get in the output of the sampler. So this is a impulse. This is how we are getting an impulse signal, impulse sample signal. So what is this? How do we represent x star of t? X star of t in mathematically, how do we represent is? It is x of 0 into del of t. Del of t is an impulse signal, plus x of capital T into del of t minus t, that is the second one. You are adding all these signals, infinite summation. You are adding all these signals, x of 2t, del of t minus 2t, x of 3t, del of t minus 3t, plus so on up to infinity. Now if you sum up all these values, what do I get? The output of the impulse sampler, x star of t, is equal to x of kt. Can I write it? Sigma k is from 0 to infinity, x of 0, x of t, x of 2t, x of 3t. So at any instant I can write it as x of kt, and del of t, you can write it as del of t minus 0, del of t minus 0, del of t minus t, del of 2 minus 2t, del of t minus 3t. Therefore, if I generalize this, I will get del of t minus kt. So this is our x star of t. When you are having x star of t is equal to sigma k is equal to 0 to infinity, and you are going with these values. Now when I apply Laplace transformations to this signal, to this equation A, for example, Laplace transform of x star of t. What is the Laplace transform of x star of t? That is, I can represent this as x star of s, which is nothing but Laplace transform of x of 0 del of t plus Laplace transform of x of t del of t minus t plus Laplace transform of x of 2t del of t minus 2t plus so on up to infinity. So you are having this as the Laplace transformations. Now what is this? X of 0 is a constant, x of t is a constant, x of 2t is a constant. When you are having that Laplace transform of x of 0 del of t, you are having x of 0 e into 1 plus Laplace transform of this, you are having x of t e power minus ts plus x of 2t e power minus 2ts plus x of 3t e power minus 3ts plus so on. Now this is x star of s. Now this same x star of s, you have it like this. If this is also a summation of infinite series, therefore I can put this like this. Sigma k is from 0 to infinity, x of 0, x of t, x of 2t, x of 3, so on. I can write it as x of kt, and you can write this as e power minus ts, e power minus 2ts. Here it is e power minus 0ts, therefore e power minus kts, if I generalize all these signals. So x star of s, you are having these two signals like this. You have x star of t, once you have understood this, you are left over with these two equations. X star of s is equal to sigma k is 0 to infinity, x of kt into e power minus kts, and x star of t, it is a train of impulses with different magnitudes at different instants. You get sigma k is 0 to infinity x of kt into del of t minus kt. Therefore, you have these two signals. When you have these two signals, now when you try and visualize, or you can have by definition of z transform of x star of t, for example, if you have, or x of kt or x of t, you have that by definition sigma k is 0 to infinity x of kt z power minus k. Now when you compare these two equations, everything is one and the same. That is, this z transform of x of t, it is x of z. Then x star of s is equal to sigma k is 0 to infinity. You can just compare these two, x of kt, e power minus kt is z power minus k. Therefore, if I replace z with e power ts, if I replace z with e power ts, then a Laplace transformations and z transformations, you can understand that there is some reference between z transformations and Laplace transformations. With this linearity, that is z is equal to e power ts, that is the relationship between z and s. Both are complex domain variables, z and s. S is sigma plus j plus or minus j omega, and z is a complex variable which has got a real part of z and an imaginary part of z. Therefore, both are complex variables, and t is the sampling period. So this is the t is the sampling period with which you will have to sample the given continuous time signal using the impulse sampler that we have already discussed today. So z is equal to e power ts. Now you can say that what is s when compared with z? You can say if I apply natural logarithms to this, I will get 1 by t ln z. Or you can say ln z dot ts, s is equal to 1 by t, or I can write it for you, ln z is equal to ln e power ts, and ts comes back, you have this natural logarithms, therefore you have ts ln e to the base c, e to the base c is 1, therefore what is s? 1 by t ln z to the base c. Now using this representation, I can say that x star of s, when s is equal to 1 by t ln z, when this is occurring, you can say that this sigma, this is equal to x of z. That is the Laplace, the starred Laplace transform, you can call it as the starred Laplace transform of the function continuous time signal x of t, which is equal to x star of s, when s is equal to 1 by t ln z is equal to x of z. That is a Laplace transform of any train of impulses, if you are considering it, that is equal to the z transform of the function x of t. Right. So we have this in mind, and we can remember these two equations. X star of s is equal to sigma k is 0 to infinity x of kt e power minus kts, and x star of t is equal to sigma k is from 0 to infinity x of kt del of t minus kt. Now del of t minus kt is our train of impulses. So with this in mind, we already understood what is an impulse sampling. With this in mind, we can go with the data hold. What is a data hold? Data hold is the process. It is a data hold circuit. You can also use a circuit for data hold. So I will put the heading as data hold circuits. Data hold circuits helps us in the process of converting or reconstructing. You can use the technical term reconstructing the continuous time signal and which I will name it as h of t, because it is a whole circuit h of t, from a discrete time sequence x of kt. You can understand this. Already we have discussed that we are having a continuous time signal x of t. When it is applied to a sampler, you are getting x star of t, or you can call it as x of kt. Now you are having this. When this is given to a zero order hold or a data hold circuit, when you are going with the data hold circuit, you are going to get a h of t, which is again continuous time signal. Now this is a continuous time signal. Now this is a sample data signal, or a signal that is having values only at discrete instance of time. So you are calling it as x of kt, that is k from 0, 1 to so on up to infinity, and data hold circuit is a circuit that is converting this discrete data sequence, which is having values only at discrete instance of time, into a continuous time signal again. So that is called, you are trying to convert back or reconstruct back the continuous time signal from a discrete time sequence. That is called data hold circuit. Data hold circuit is the process in which we are trying to reconstruct the continuous time signal h of t from discrete time sequence x of kt. So for this we will try to understand how do you reconstruct back a continuous time signal from a discrete data sequence. For example, let me say I have kt 0, k is from t, k is from 0, 1, 2, 3, so on, 3t, 4t, so on up to infinity. Now for example, let me say we have a continuous time signal, any of that sort. I have this signal here, I have one more signal here, an impulse sample. Now this is our x of kt, right? So we are having somewhere of this form. Now what is it? There are many forms of data hold circuits. One form which we can directly understand is, if I can try to hold back this amount of signal, this signal up to the next, that is, this is the first instant which I am working on, and until the next instant I don't have any information. Therefore what I try to do, I use a form of a capacitor so that I can hold this data until the next instant. Already we have discussed the sampler and hold circuit. A circuit diagram is given to us, and there we will be using a very high quality capacitor which is having very low leakage coefficient. Therefore it can hold the circuit, hold the value of the signal, at this instant until the next instant. Similarly, at this instant, what is the value of this magnitude? That is until this point. So this value can be held by the circuit until the next instant. That is, you are working on two instants at a time, t and 2t, or 2t and 3t. That is, that value before that if for example if I say this is kt and this is k plus 1t, right? Between any two instants, what is happening? We are holding the previous magnitude instant until the present instant. If you are working on k plus 1t, this is our immediate instant, then the previous instant can be considered and it can be held up to the next instant. And similarly, I am holding it until the whole circuit is holding it until the next instant. And here what is happening? It is holding this value until the next instant, and similarly it is holding it until the next instant. It means that you can say, if you are trying to reconstruct back, that is, you can call this as a staircase generator. A data hold circuit can also be called as a staircase generator, or it also works like a clamper. It works like a clamper, or it works like a staircase generator. Now you can see that we are only trying to approximate the continuous time signal. For example, if this is our continuous time signal, then we are only trying to approximate the reconstruction process. Data hold circuits are trying to reconstruct. So this reconstruction process is an approximation process. Reconstruction is approximation. So the reconstruction that is done by data whole circuit is nothing but an approximation. Therefore, you are trying to get it in this way. So you can say that h of kt plus t. Now, if I consider h of t plus kt is equal to x of kt. Right. So you can also, otherwise you can take another variable h of kt plus tau is equal to x of kt. Right. Tau is the time delay. You can say x of kt. Therefore, that is the next instant kt plus tau. Tau is a time delayed function. Therefore, you are trying to get the value until the next instant. Therefore, the previous instant value will be considered here. Now, it is working on kt less than or equal to kt is between tau is between kt and k plus 1t. When this is happening, when tau, the value of tau is in between kt and k plus 1t, that is for example t and 2t or kt and k plus 1t, then this is happening. That is h of kt plus tau, the next instant the magnitude will be considered until the next instant. You can say that the value is held by until from the previous instance. So therefore, reconstruction process, you can say this is a very simple zero order hold. You can say this is a simple zero order hold. You have nth order or even higher order data hold circuits. So that data hold circuits, you can call this by the h of kt plus tau when you are going with the reconstruction process by a polynomial extrapolator. A data hold circuit can also be called as a polynomial extrapolator circuit. Right. So h of kt plus tau can be called as, or a data hold circuit can be called as a polynomial extrapolator. That is, we are trying to get back a continuous time signal from a discrete time sequence. Therefore, this, if you are representing it in an equation form, when you are representing it in an equation form, you can say h of kt plus tau is equal to an tau power n plus an minus 1 tau power n minus 1 plus so on plus a1 tau plus a0. a1 tau plus a0. Now, when you can call this as an nth order polynomial extrapolator. Now, when n is equal to 1, you can say it is a first order hold. You can also call the nth order polynomial extrapolator can also be called as an nth order hold. Now, when n is equal to 1, you can call it as a first order hold, and when n is equal to 0, you can call it as a zero order hold. So, for this case, when n is equal to 1, when it is first order hold, you can say from this, when n is equal to 1, you can say a1 tau h of kt plus tau is equal to a1 tau plus a0, and h of kt plus tau is equal to a0 when you are going with n is equal to 0, because n is equal to 0, you are having zero order hold h of kt plus tau. From this equation, you can get that h of kt plus tau is equal to a0, and for n is equal to 1, which is a first order hold, you can have h of kt plus tau is equal to, when n is equal to 1, a1 tau 1 plus a0, 1 minus 1 tau n minus 1. Therefore, you are having a1 tau plus a0. So this is a, now we will try and understand what is this. Now, I have already represented h of kt plus tau is equal to kt, which is giving us a staircase generator. That is what we have already used here. Right. Therefore, a0 can be called as x of kt. So, a0 is obtained from the previous instant of the continuous of the discrete time sequence which you are working on. That is x of kt. When you want the value of x of k plus 1t, then you are going to work on different the previous instant. Therefore, you are having for many time delays. If you are increasing the time delay, what is happening now here? What is the difference between n is equal to 0 and n is equal to 1? This being a zero order hold, it doesn't have any time delayed for constants or time constants. Here when n is equal to 1, you are introducing one time delay, a1 tau plus a0. When you are going for n is equal to 2, you are going with h of kt plus tau is equal to, it is a second order hold, you are going with a2 tau square, a1 tau plus a0. Now this has become a quadratic equation, and if you are changing the values of tau, you are going to get two values of tau. If you are going to change the values, that is, you are having two different values of time delayed functions. When you are introducing time delayed functions, then what is happening? The accuracy of the system might increase. Accuracy of the system will increase, but the stability of the system decreases. Stability decreases, accuracy increases. When the time delayed functions are increased, number of time delays are increased in the system, accuracy of the system increases, but there is a very big problem that stability of the system decreases, or it might also lead to instability. There is a reason why we are not going to go for higher number of time delayed functions, that is beyond first order hold or beyond zero order hold. If we try to go, we are trying to lose the stability of the system, which we doesn't want it in control systems, because you are trying to control the system, and the most important thing, parameter that we are going to control is the stability. That stability should not be decreased. Therefore, we are not going for higher order in data hold circuits. We are only going for zero order hold circuit. Throughout the length of this lecture series, we are trying to deal with only zero order hold. At times, if necessary, we will go with first order hold circuits. Therefore, let us see what is the zero order hold now. Now we are going to discuss a zero order hold circuit. Zero order hold. Let us see, for example, I have this diagram. I have x of t, which is our continuous time signal. For example, let us say we are having it like this, and time t0 x of t. This is our signal, and here I am trying to give a impulse sampler. This is a sampler with time del t, which is a sampler. It might not be existing, but in the real world, but for mathematical applications, we are trying to use this del of t. Then you are going to get x star of t. You can also say discuss this with x star of s, because we have already discussed x star of s. What is x star of s? This is the star the Laplace transform of x of kt, where you will be getting that signal, the value, the equation of which is sigma k is equal to 0 to infinity x of kt del of t minus, e power minus kts. And here, if I apply zero order hold, now what is the signal that we are going to get? X of kt, right, and at different instance of time, we are going to get it here 0t, 2t, 3t, 5t, 6t, etc. You are going to get x of kt here. In this one, this x of t, when you are applying to the sampler del t, then you are going to get x star of t or x of kt or x star of s. Then x of kt, you can represent it as in this form, and if this signal is applied to the zero order hold, we are going to get this signal, that is t again. You are going to get h of t, and this is the signal. Right. So you are getting a staircase signal, staircase generator, or a clamper. right? So we are having, this is a zero order hole circuit. This is the output of a zero order hole. Therefore, you are going to discuss what is going to happen in this zero order hole circuit. What is the point in discussing with a zero order hole circuit? Now you can see that any signal which is having a simple, we are going to discuss what is the transfer function of zero order hole. Transfer function of zero order hole. You can call it as zero order hole. Then the transfer function of zero order hole, you can say, for example, if I have ZH naught of S is equal to 1 minus e power minus Ts by S. This is what we will have to prove. What is GH naught of S? That is the transfer function of zero order hole. Now what is happening in this zero order hole is what we are going to try to discuss. GH naught of S is equal to 1 minus e power minus Ts by S. This is what we will have to prove it here. Therefore, let me first discuss H of t. H of kt plus tau, or H of t, you can call it as H of t. H of t, how do we represent H of t from this diagram? That is t, 2t, 3t, 4t, 5t, 6t and so on. Now H of t, I can say it is nothing but x of 0 into, now x of 0 will give you the magnitude and it will give me 1 of t minus 1 of t minus t. For example, I have a unit step signal, that is nothing but 1 of t. Now I have a signal which is existing, a unit step signal which is existing from t is equal to capital T. Now how do you represent this? 1 of t minus t. Now if I subtract 1 of t minus t from 1 of t, that is, if it is from t, I have one more signal here. Now if I subtract these two, 1 of t minus 1 of t minus t, what is the value that I am left over with? I am left over with, these two are the common terms, so I am left over with only this signal. So this is the signal that we are going to, I am trying to represent this signal with 1 of t minus 1 of t minus t. And what is the value of this signal? It is 1 of t minus t minus 1 of t minus 2t. Therefore, I can add that signal here, x of t into 1 of t minus 1 of t minus 2t. Right. So, you have x of t, you have these two signals. Now what is the third signal? You can say x of 2t into 1 of t minus 2t minus 1 of t minus 3t plus so on. So x of t, x of 0, x of t, x of 2t, all this gives you the magnitude. The magnitude of that signal. This is x of 0, x of t, x of 2t is this much, x of 3t is this much. So into 1 during that period, during t and 0 and t. During t and 2t you have the magnitude this much. During 2t and 3t you have the magnitude x of 2t. So you are going to have this signal continuously, and with this zero order hole, now we are going to apply h of t is equal to, it is the sum of sigma, it is also an infinite summation, k is from 0 to infinity, x of kt into 1 of kt minus 1 of k plus 1t, 1 of k plus 1 t. That is a summation of infinite number of values. So you are adding all these values, infinite values, into this single signal. Now we know that what is the Laplace transform of 1 of t? It is 1 by s. What is the Laplace transform of 1 of t minus t. That is a time delayed function with magnitude with value t. You can write it as e power minus ts by s, or Laplace transform of 1 of t minus kt. I have it as e power minus kts by s, and Laplace transform of 1 of t minus k plus 1 t. I have it as e power minus k plus 1 t s by s. Now if I represent, if I substitute all these values here, x of kt being a constant, I can say that we have h of s is equal to sigma k is 0 to infinity x of kt, which is a constant, therefore it can be taken out of the Laplace transformations. Therefore what do I get here? I get e power minus kts by s minus Laplace transform of 1 of k plus 1 t. I have e power minus k plus 1 ts by s. Therefore h of s, I can write it as x of kt is inside the function, therefore I can consider sigma k 0 to infinity x of kt, and the denominator is s, and if I take e power minus kts common, I have 1 minus e power minus ts. Therefore if this is this part I can take it outside because it is nowhere related to k. Therefore I can say that it is e power minus ts by s into sigma k 0 to infinity x of kt e power minus kts. This is our h of s. So if we consider this equation, now if we consider this equation, I can say, can this be our transfer function of the zero order hold? Now we are trying to discuss the transfer function of the zero order hold. Now let me say we are having zero order hold. Let me say I am having x of t and the sampler with time period t and x star of t or x star of s. Let me say we are not going with this one, and let me say I am getting a function h1 of t. Now h1 of t is our continuous time signal obtained from the zero order hold, which is applied to the a discrete time sequence is applied to the zero order hold. The output will be a continuous time signal. Therefore now let us consider again similar x of t, del t of t, x star of t, x star of s, and for example let me say zero order hold is got the transfer function gh0 of s, and let me say it is h2 of t. Now using this I am getting this h1 of s. Now if this is it, because I have used zero order hold, now I will only have to find out whether 1 minus e power minus ts by s is equal to gh0 of s. Now we have got this x star of t, zero order hold, when I have applied x star of t or x of kt to zero order hold, I am getting h1 of t here. Therefore I will write it as h1 of s. Now this is h1 of s when you call it as x star of s. X star of t, you are getting it x star of s. Now when you are applying, now h1 of s, based on the second diagram, you can say that, let me say this is h2 of s, then we can say that h2 of s is equal to gh0 of s into x star of s. gh0 of s into x star of s, and we know that h1 of s must be equal to h2 of s. Therefore, when I consider this as h1 of s, then h1 of s is equal to g h naught of s into x star of s. When this is happening, now let me say sigma k is 0 to infinity x of kt e power minus kts. While deriving impulse sampling, we have already discussed that x star of s is equal to sigma k is 0 to infinity x of kt e power minus kts. This has already been discussed in our just immediate previous class. Therefore, x star of s. Now, this is the only term when you are comparing this equation and this equation. You can say that g h naught of s is equal to 1 minus e power minus ts by s. Therefore, you can say the transfer function 0 order whole g h naught of s is equal to 1 minus e power minus ts by s. So, the derivation for 0 order whole transfer function is obtained as g h naught of s is equal to 1 minus e power minus ts by s, and this transfer function will be utilized by us throughout the lecture series whenever we are going to use a 0 order whole.